then because okay. 13 through 7. So yeah, maybe Christmas or something. Anyway, I wanted to go through one example of Gaussian elimination just to refresh our memories if we've already had linear algebra. Otherwise, to show the process if we've never seen it before. And again, remember that we've got this system here. I've got three unknowns in this case, x, y, and z. And so I need at least three equations here in order to determine the system completely. And to do that, what I'm going to do is I'm going to transfer this system into an augmented matrix. In other words, all of these x's are aligned, so that's the first column. Y is the first column, z is the third column. And then, of course, we've got this. This is why we call it augmented, because we have this fourth column over here, which represents the right-hand side. Okay. So what I'm going to do is I'm going to transfer this into a matrix with just the coefficients. Now, the coefficients here are, of course, 1 implicitly. Right? So I'll leave 1, 2, and 3. And then 2, and then do keep the signs here. So if you've got negative values here, that is valid. Right? 4, 3, and we don't have an example here, but if z was not part of this equation here, then, of course, the coefficient would be 0. Right? But we'll go ahead and keep it like this. 1, negative 5. And then here's the augmented part. Sometimes people draw these with a vertical line or a vertical dotted line or something. 24, 3, and negative 6. All right? So there's our augmented matrix. Now what we want to do is we want to eventually get it to look something like this, where we've got numbers up here on the upper diagonal, and then we've got zeros down here. And then, of course, we've got numbers here as well for the fourth column. We want to get it to a form that looks something like that. Okay? So let's go ahead and start. And what you do is you work top to bottom. Copy this. All right. And paste it. There we go. And clean it up a little bit here. There we go. All right. So you work top to bottom here. In fact, what we're going to do is we're going to work on the first column. We want to make these two entries right here zeros. All right. And then once those are zeros, then we'll make this. Then we'll go to the next column, and we'll start and make this one 0. Right. If this was a much larger square matrix, then we would work on the first column, then the second column, then the third column, and then the fourth column, etc., until we get everything into an upper triangular form or an upper echelon form, or whatever terms there are several terms out there. So remember that I've got those basic operations that I can do. I can, of course, swap rows. I can multiply a row by a scalar, right? Any c here. Why? Because I can go ahead and multiply each one of these things on the right-hand side by c, and I can multiply as long as I multiply the right-hand side by c. I could exchange columns, but that's not going to be too useful because then that would exchange the variables. I can subtract one equation from another equation, and then I can do that in combination. So I can multiply one equation and then immediately subtract it off from another equation. So with those basic rules in place, or those basic operations in place, what would I have to do to this one, this entry right here, in order to make it into 0? With respect to the first row here, because I don't want to do anything with respect to the bottom row here, because eventually I want to make that 0 as well, right? If I go and modify this and then modify this, I'm just going back and forth, and I'm resetting them to non-zeros every single time. So what do I need to do to the second row with respect to the first row to get this entry to 0? Subtract 2 times the row 1 from row 2. Okay? So let's do that. The first row, of course, will stay the same, 1, 2, 3, and 24. Okay? So if I multiply this by 2, I get 2, 4, 6, and then 48, right? And if I take that off of this row, what do I get? Well, the whole purpose of doing this was to make that 0, right? Subtract 2 times 2, right? is going to be 4, but subtracted from -1 is going to be -5. 2 times row 1, 2 times 3 is going to be 6. Subtracted from 1 is going to be -5 as well. Right? And don't forget the last one, right? That would be like manipulating an equation on just one side. You have to manipulate it the same way on both sides for the equality to be maintained. So twice over 24 here is going to be 48, but subtracted from 3 is going to be -45. Right? Help me out with my math, because I might be wrong. And then also, that's the first part here. 2, how do I make this guy right here into a 0? I subtract 3 times row 1 from row 3. When I do that, again, the whole purpose of me doing this is to get 0 here. 3 times 2 is 6. Subtracted from 4 is going to be -2. 3 times 3, 9. Subtracted from -5 is going to be -14. 3 times 24, 72. Minus, subtracted from -6 is -78. There we go. Great. Now I've got this first column here where it's all upper triangular. These are all zeros except for on the diagonal here. We want to let that remain whatever it was before. Okay. Now, we take this. Let me copy that. Copy and paste. Now let's work on that more. Right? Now what do I want to do to get rid of this element right here, to make this one 0? I could do it with respect to row 1 again, but what will that do? That'll screw up my 0 right here. Right? And it'll screw up my 0 right here, I guess. Right? So I don't want to do that. I want to do it with respect to row 2. So what I'll do is I will say, what's that going to be? Subtract 2 point, I guess what is it going to be? Oh, well, that's Gaussian elimination. I don't want to do that. But you could, so one observation here is, I don't want to have to think about that. What you could do is you could normalize this, divide this by this entire row here. You could multiply it by -1/5. That'll give you one. That'll end up giving you ones all along the diagonal, right? Which is nice, but I don't want to go that far because that's more code. Right? So what times row 2? Subtract x times row 2 from row 3. 2/5? 2/5? Why? Because 2/5 times -5 is going to be -2, but subtracted from -2. So we want -2/5, right? -2/5 times 5. Oh, sorry. You're right. Subtract plus whatever, right? All right. So the first 2 rows are unchanged here. 24, 0, -5, -5, -45, 0, and then of course 0. So subtract 2/5 times 5. That's going to be, help me out, -2. Subtract that from -14 makes it -12. Yes? Okay. 2/5 times -45. Yep. 9 times 2, 18. So -18, but subtracted from 78 is going to be 60, -60 still. Right, there we go. We're done, right? We've got this in upper triangular form. Now, look at what that looks like with respect to the equations. Just look at the row 3 here. We've got -12z is equal to -60. We've got one equation with one unknown. What can we do? Yeah, just take that z is equal to -60 divided by -12, which is 5. Right? Now go up one row. This is this was row 3. Now go up one row to row 2. We have that negative 5y minus 5z is equal to negative 45. Right? But guess what? We've already solved for z. So if we plug that back in over here, then this just becomes a number. This is negative 25. So how do we solve for y? Well, take negative 25 onto the other side. Plus 25. And then divide all of that by negative 5. That's going to be negative 20 divided by negative 5. That's going to be 4. Right? Y is equal to 4. There's our first solution. There's our third solution. And then you can do the same thing for the first row. Why did I start from row 3 and go up to row 1? Well, because it was upper triangular. It's called back substitution or back solving. Once we've got it into an upper triangular form, we go backwards to actually solve for z, y, and then x. Okay? So now let's think about this. Oops. Preview. Let's think about this more generally. Where are we? Let's think about this with respect to a larger matrix here. And what we're going to do is we're going to jump right into the middle of the algorithm. Okay? So if I've got this big matrix, presumably I've already done row 1, row 2, row 3, dot, dot, dot. Now I'm considering the ith row. How do I go about doing that? Right? All of these are going to be 0, so I don't need to worry about those. What I need to do is I need to look at a sub ii, which is on the diagonal here, and I need to make everything below it 0. Okay? To do that, let's jump into the middle of that algorithm, right? Where I'm looking at the jth row right here. How do I make that entry 0? Right? What I need to do is I need to compute t, which is going to be this value divided by this value, because that's what I'm going to subtract when I multiply it by this value from that value. Right? So I use t is equal to whatever their ratio is, so that when I take this value and subtract t minus this thing up here, I get 0. That value is what I use for everything else on that row. So for k running from I to I plus 1, I plus 2, dot, 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 up to n plus 1. Why n plus 1 if I start at 0? Remember, it is not an n by n matrix. It is an n by n plus 1 matrix because it's this augmented matrix. Right? There were 3 equations and 3 unknowns, but I had this augment, this additional column in the end that corresponds to the right-hand side. And there's that number right there. Okay? So this formulates the basis of the algorithm that we have to do, right? For each row, from 2 up to row n, the last one, what I have to do is I have to make each column I, and if I give this an I here, I plus 1 up to n zeros. Right? So I've got this 4, and then I've got this nested in here. Now, how do I make it 0? Well, for each entry, k, dot, 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 make it 0 by doing this equation down here. So that kind of suggests 1, 2, 3, 4 loops here. Right? That's what I'm going to have to do. For each row, for each column, row under that row, in that column, you have to make that entire row, well, the first one's 0. Hopefully none of the rest of these become 0, because we'll talk about that in that situation here in a second. But you need to change all of the things in that row. Okay? Without having to write it from scratch, let's go line by line with the pseudocode that I provided in the book. So first of all, we're given an n by n matrix and a 1 by n vector b, which is the solution vector on the right-hand side. Our output is going to be an augmented upper triangular matrix A prime preserving the solutions. So in other words, it's not going to do any illegal operations. Okay? First of all, we create our augmented matrix by simply just taking the original matrix and then putting that, that column there as the last column. Okay? Now what we're going to do is for each row, for each I is equal to 1 up to n minus 1, we do that, is that right? Yeah, that's right. Yeah, because we're going to use that row as our pivot, our element that we're going to take away from everything else. So we don't have to go all the way up to n. Why? Well, because the last row will already be taken care of. Now, here's a little bit, the next few lines here are going to be different from what I just presented. I'm going to just go ahead and go forward and annotate these. So what this process is doing is it's finding the row with the largest magnitude. That's where this is coming in right here. What we're doing is we're going to, our pivot row here is I. And then we go through all of the other rows, all of the other elements down below here, and find the largest one with respect to absolute value. Okay? That's why we're taking an absolute value here and here. And then at the end, what we do is we swap it. So all we're doing is finding the row here with the entry that's the largest value here, and then we're swapping it and row I. Remember that we can do that. Why? It's one equation and another equation. Does it matter if we write what order we write them in? Nope. So I'm going to swap those. Why do we do this? This is to reduce floating point errors. What we're eventually going to do, remember, is we're going to take that value, ace of I here, right? Once we move that up, then we take that value, where is it? There we go. And we multiply it by this t over here, which is also divided by it. But if we're multiplying and dividing by small numbers, basically that leads to floating point errors and round off errors and stuff like that. Not an issue with Python. Python, you could probably get away with that. So if you really want to omit this part right here in a Python implementation, it's probably going to be okay. If you were doing this in, say, C or something else, you would definitely want to do this. This is called better Gaussian elimination, right? And it's just to reduce floating point errors here, right? If you're going to do this in Python, what I would suggest, since this is really easy to translate to actual Python code, try it with, try it without, and see if it makes a difference. All the answers on the grader were written in Java, I believe. So see if it makes a difference. Right. Here's the actual work. Right. So for each row, remember we said for each row, right, we are going to compute t here, which is the jith element, then for each column after that, for each j running from I plus 1 up to n, we find that t because we need to subtract the row value times t from the row value. To make that, now for the first one, that's going to end up making this 0. For all these other values in this row, it's going to change them, but hopefully they're not 0. Okay? And that's it. We output the augmented matrix at the end. That's only the first part, right? That only gets us to an end that looks like this. What about all this stuff, the back solving, right? Let's think about that generally first of all. I want my equation here. All right, so let's think about how we did this with this particular example, and then let's generalize it. So for this particular example, if I've got, say, I've gotten down here to the last element, and it's a sub, what would it be? N, and then b sub n is over here. Remember, this is the augmented matrix. Okay? Let's think about the first solution here. How do I solve for xn? Well, draw this equation out. What is this? This is a n n times xn is equal to bn. So what's the solution for xn? Oops. Xn is equal to bn over ann. That's the first one. Now think about the next one, or the one above that, as you work your way up. This is going to be n minus 1, n minus 1, and this is a sub n minus 1, n. And this is b sub n minus 1. How do I solve for that? How do I solve for x of n? Again, this equation right here is going to end up being corresponding to a sub n minus 1, a sub n minus 1 times x sub n minus 1 plus a sub n minus 1, a sub n, xn is equal to b sub n minus 1. All right? So solve for this guy right here. Well, I need to take this onto the other side and then divide by this. So this will be b sub n, or sorry, x of n minus 1 is equal to b sub n minus 1 minus a sub n minus 1, a sub n, xn, all over a sub n minus 1, a sub n minus 1. One more, bear with me, because I want you to start seeing the pattern here. Right? Here's the first one, here's the second one. Let's do one more, and then we will generalize this. Right? So look at the last, look at the third to last. Right? It's going to be a sub n minus 2, a sub n minus 2, a sub n minus 2 is the same row, a sub, or n minus 1, a sub n minus 2, a sub n, and then b n minus 2, right? And then these are all zeros, dot, 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 and there's your diagonal, right? So this corresponds to the equation a sub n minus 2, a sub n minus 2, x sub n minus 2, plus a sub n minus 2, a sub n minus 1, x sub n minus 1, plus a sub n minus 2, a sub n, x sub n is equal to b sub n minus 2. All right? Solving for this guy right here. What do? Take this one and this one onto the other side. So I've got that x of n minus 2 is equal to b sub n minus 2 minus a sub n minus 2, a sub n times xn minus a sub n minus 2, a sub n minus 2, 1, xn minus 1, all over a sub n minus 2, a sub n minus 2. All right? That was for the third one. Right? This was for the first one. This is for say j is do I use j? What do I use? Bear with me. Looks like I use, yeah, j. For j being 1, this is for j being 2, and this is for j being, actually, sorry, we're going backwards, aren't we? This is for j equals n, this is for j equals n minus 1, this is for j equals n minus 2. So now generalize this. If I want to solve for x of let's see, what do I want? X of I. What's it going to be? That thing on the right-hand side, b sub I, minus, and then I need to run through each one of these. This one and this one, this one, this one. How is it changing? This one is the same subscript as the first one, right? On all of these. So this is going to be a sub I. What about the second subscript? N minus 1, n minus 2, n minus 3, until when? A sub I plus 1, x sub I plus 1. Come on, there we go. Minus a sub I plus 2, x plus, of I plus 2, right? minus dot dot dot. The last one will be the thing on the same row, a sub n, x of n. This is the last variable, second to last variable, dot dot dot, and then the variable right that you solved for right before. Don't forget your denominator. What goes down there? A sub I. There we go. Right. So all you have to do is do this for I running from n, the last variable, all the way back up to the first variable. Right. And why do you have to do it in reverse? Well, because it's upper triangular, right? You have to work from the bottom up. Go ahead.
Can you go back to
Did I do them out of order?
Yeah, I think so.
That's okay. Minus A minus B is the same thing as minus B minus A. I just did it in this order so that I could write this nice loop here, which gives us the following algorithm. Back solve. There we go. So once we have that augmented matrix from the original Gaussian elimination here, right, then what we can do is we can plug that in to this back solving, and all we have to do is run I from n up to, oops, I didn't mean I meant 1. There we go. N down to 1, and we set this last one to b sub I, this thing right here. And then for j running from I plus 1, I plus 2, dot dot dot, up to n, we simply subtract off whatever terms we had here, right? So this is a sub I j times x of j, and then we subtract that off of t. Right, the t here is our total. That's why I use t, or temp, or something like that. And then at the very end, we divide by it, divide by that value on the diagonal. Yeah, go ahead. Okay, so this one I was using mathy stuff. I see what you're saying. Yes, I screwed up. Comma. There we go. Was I doing that on the other slide too? Yeah, okay, all right. Comma. There we go. Down here, I'm using this kind of notation here, which is pseudocode two-dimensional matrix multiplication, or syntax, whatever. If you were doing when you go to do this in Python, of course it'll be a two-dimensional array. If you want to do it that way, that's what I would say, right? So when I write I comma I plus 1 here, I mean something like this in Python, or when I write something like this in pseudocode, I mean something like this in Python. It's just a two-dimensional matrix. Yeah. Yes. So the 8th, is it? No, the 7th. Yeah, whatever it is. Yep. But I mean, it's pretty simple. All you have to do is transcribe this. Again, this one is kind of optional, because Python has multi-precision built in natively, so you don't necessarily need to worry about round-off errors, floating point errors. It'll take care of it for you. But I would suggest that you go ahead and try this and see if it does make a difference if you're using Python. If you're using C or something else where you've got 32 or 64-bit floats then that are susceptible to round-off errors, then yeah, you probably want to use something like this. I think in the end you just have to report it out to like 6 digits of accuracy, 6 decimals of accuracy, so or close to, or something like that. I do want to take a look at the analysis of this though. Where's my algorithm? There we go. So repeat this algorithm here. Let's go ahead and analyze this. Oops. So what's our 5-step process? What's the input? What's the input size? What's the elementary operation? And then analyze it with respect to the elementary operation. So it's clear that our input here is going to be these two things, this matrix and this vector over here. So what is the size? So here's where you can, kind of fudge it a little bit. First of all, we've got two inputs, right? Well, let's go ahead and just simplify that to the first one. Why? Because it's much larger, right? N by n. So is it an n by n matrix so the size is n squared? Or should we only consider one dimension n? Neither one is wrong, by the way. Right? It's only it'll only affect the analysis at the end. Right? So if I were to do the first one, what I would say is, okay, I'm going to give that a different name so that I don't have that square there anymore. Big N, right? Versus little n here. Let's do it this way, though, first, and then we'll come back and see how it affects it if we did it the other way. Okay? What's our elementary operation? $12? Okay. I like how you said just line 12, right? You didn't say subtraction, you didn't say multiplication, you didn't say assignment, you didn't say a lookup in your matrix or anything like that. Who cares? It's just one line, right? You do one multiplication, one subtraction. So at the end of the day, if you choose one or the other, is it going to make a difference? No, it's just this one right here. Right? So here's my elementary operation, line 12. I'll just say multiplication. Okay. So how many times is line 12 executed with respect to the input size? Well, it's executed for k running from I up to n minus or n plus 1, and we do one multiplication for each one of those. That entire thing is executed for j running from I plus 1 up to n, and then that entire thing is executed with respect to I running from 1 up to n minus 1. Do we want to solve that? We've got time. Anybody want to see the solving of that? I don't want the entire thing. I just want you. Come on. Copy. Come on. There we go. Do we want to solve it or not? Okay, let's solve it. Let's solve the inner part first here. That was a plus, right? Okay. Didn't get copied over. So let's just solve this part here. 1 plus 1 plus 1 plus 1. How many times? Careful. You start at I and go up to n plus 1. So this is going to be n plus 1 minus the things that you didn't add, which is I minus 1, right? Because you are adding I plus 1, I plus 2, I plus 3, right? And then preserve your other summations here. J is running from I plus 1 up to n. What was the first one? I is equal to 1 up to n minus 1. Right. So simplify this one first of all for me. What does this end up being? Move it over here. So n plus 1 minus 1, so it's plus 2. Right? So this ends up being n minus I plus 2. Right? Summation of sums is equal to the sum of summations. So let's look at this one. We can break this up into 3 summations. J is equal to I plus 1 up to n of n. J is equal to I plus 1 up to n of I. And we subtract that out. I'm just going to take the subtraction out front immediately. Plus summation of j is equal to I plus 1 up to n of 2. So solve each one of these. The first one, it's n plus n plus n plus n plus n. How many times? Not n times, but n minus what? N minus, we start at I plus 1, so The things that we didn't count were 1 through I. So n minus I times n, right? What about this third one right here? 2 plus 2 plus 2 plus 2, how many times? N minus I there as well, times 2. What about this one right here? Yeah, I plus 1, I plus 2, I plus 3, all the way up to n. Ugh. That's Gauss's formula, right? Summation of I equals 1 up to n of I is equal to n times n plus 1 all over 2. But that's not what this is, right? We start somewhere else. So what's the summation of I from 1 up to I? We need a different variable there. Right? In fact, did I screw up? I shouldn't have used I there, I guess. What did I use? Oh, I should have used K. All right, that's fine. This ends up being J, I think, right? At this point, I don't want to solve it. So, how can I solve it if I don't want to show my work? Come on, where are we? Come on, why can't I go back over here? What the heck? Okay, there. Now I'm back in control. So, Wolfram alpha. Can Wolfram alpha solve this? Sum of let's see. I think how do we do sums? Sum of say 1 k is equal to I up to n plus 1. Is that the syntax? N plus 1, sorry. There we go. There. Was that our first solve? N minus I plus 2. Yep. All right, now put that sum into another sum. Sum of j equals I plus 1 up to n with the first sum. There we go. There we go. And now what's the sum of that? Sum of that with I running from 1 up to n minus 1. There we go. All right. Wolfram alpha. What's the takeaway from that, though? N cubed, right? So go back over here and copy that down. Dot, dot, dot. We get 1/6. Yeah, I know. I'm not going to be able to copy it unless I see it here. Let me copy it, and then we'll take a look at it. Minus 5. There we go. All right. So what's the highest order term here? This is 1/6 n, or 2/1/6 n cubed, plus, and then lower order terms right here. We ignore this constant right here, and we take this one, and so it's going to be order n cubed. All right. Now, as we've seen before, is n cubed acceptable? We know that n squared is not acceptable for large amounts of data. Think about this, though. What if we'd gone a different route? What if we'd gone for n squared here instead? Right. Then what's our real behavior? Yep. Order n to the 1.5, which is kind of acceptable. Right. A million by a million matrix? Sure, you could probably solve that pretty easily. Right. I don't know how big we get in the grader, maybe like 10,000 by 10,000 or something. You're not doing it by hand. But you do need to be careful. Right? With our last 10 minutes here, let's look at some other exceptions. Let's look at some small systems, excuse me, here. 7y is equal to 8, and 2x plus 14y is equal to 16. Yeah, go ahead.
You said a million by a million, so a million would be the
Well, that's probably too much. Because a million times a million is going to be what, 1 trillion entries? Now you're talking about terabytes. I'm not storing terabytes on the on the web server there.
So the input is 10,000 by
Something like that. Yeah, it could be. It's randomized, so there are some large test cases in there. You may not necessarily get them. Just run it multiple times, and you'll get random test cases each time. Solve this system. All right, so Gaussian elimination, let's get rid of this thing right here. Twice this line subtracted from this line is going to be what? Yep. So what are we going to get? 0 is equal to 0. Right. It's unsolvable. It's indeterminate. Right. There are an infinite number of solutions. Infinite number of solutions. Right? It is 2 unknowns with 1 equation. This second equation here is just 2 multiplied by the first equation. Right? So all this is 1 line. And how many points are there in a line? Infinite number. Any point on that line is going to satisfy this equation right here. Gaussian elimination. How do you know if you have an indeterminate system? What's it going to look like in the end? Well, what did it look like here when we did the simple matter, or the simple subtraction here? What did the last row look like? All zeros, right? If the last row, or any row for that matter, becomes all 0, then you have an indeterminate system. Right? Let's look at one other. X plus 2, or x plus 7y is equal to 8, and 2x plus 14y is equal to, I don't know, 20. Doesn't matter. Do the same trick. Subtract 2 times row 1 from this row. What do you get? 0 is equal to 4. Is that true? No. This is an inconsistent system. Visually, what does this represent? Parallel lines, exactly. We've got these 2 lines here. Those 2 lines, well, I can do that better. There we go. And roughly there. Yeah, there we go. Those 2 lines are parallel. Do they ever intersect? No. Therefore, there is no solution. There's a solution there, a unique solution, if you've got 2 equations, 2 unknowns, and they intersect at exactly 1 solution point. With this one, there's not an infinite number of solutions. There are no solutions. It's an inconsistent system. Gaussian elimination. How do you tell whether or not you get this situation? All zeros except the last column. Right? So you've got all zeros in the last, you do Gaussian elimination, all zeros in the last row, or all zeros in the last row except for the last one. That's going to give you an inconsistent system. Right? Or if you ever divide by 0 either. Right? If you divide by 0, what happens? That means that you end up, where is it? There we go. If you divide by 0, what happened? This thing was 0. And you never exchanged it with a row that was larger in magnitude. Right? So that means that you've got an inconsistent system of some sort, inconsistent or indeterminate. And then you have to look at the rest of the row to determine which one is the case. Are they all zeros? And then this is non-zero, or are they all zeros? And that's an indeterminate system. Right? Okay. Any questions?
Do we check for that?
You have to, yeah, you have to. I give you several examples like that. In fact, that could be one of your test cases. I mean, you could take these test cases, this test case right here that we started out with, and there's your test case if you want. We know what the solution should be, or at least most of the solution. If you want to, you can run it through NumPy. I think NumPy has a num, N-U-M-P-Y. It's a standard Python package with a bunch of numerical stuff. I think it has a linear solver. I'm not sure. Does it? NumPy linear solver. Yep. Linear algebra dot solve. Right. You can go ahead and do that. You can use NumPy to represent your matrices if you want to. That's up to you. But what you can't do is just you can't just use dot solve and be done with it. Right. That's cheating. Right. Oops. Oh, where are we? Yeah, you want you actually have to implement this algorithm right here. Right? This pivot row stuff here, that'll also help you to try to detect indeterminate or inconsistent systems, because you're guaranteed that you only have to check it at the last row, I believe, if you have this pivot row stuff, because you're always finding the one with the highest magnitude and putting it up here. I suppose you could say that if there are no rows with zeros at all, you could stop immediately and say it's either indeterminate or inconsistent. Right? If you never actually find a row to change. Right? Any questions on that? Oh, yeah, yeah, you could do a list of lists. I don't have a quick way of doing that in the next 3 minutes unless this loads up really quickly, but okay, there's an incident anyway. Yep. Anyway, yeah, let's write some Python here. Oops. Python by hand. So if you have a is equal to, what is it going to be, list like this, right? Then for I in range of, I don't know, n, right? Then we can say that array sub I is equal to a new list. Now, you don't have a guarantee on here that these are going to be square. I mean, these are going to be square matrices, but what you if I added 3 things to the first list and I added 4 things to the last list, right, it's obviously not going to be square. But if you write it correctly, then you should be okay. Are there other shortcuts that anybody else knows of? Like after this, you could of course go array sub, 0, 0 is equal to 42. Right? I'm not giving misinformation here, right? That you can do this in Python, right? Yes? No? I'm pretty sure. I thought you guys were better at Python than I was. Okay, I'm not going to be able to do that. 1 minute. Can I just do it natively here? So, touch test.py emacs test.py. Oops. No Emacs. Oh, damn it. vi test.py. And now I'm going to have to remember vi too. So, there we go. A array is equal to that for I in range of 5. I'll just hard code it here. Array sub I is equal to this, and then for I in range of 5. Oh, you know what? Let's do it inside there as well. For j in range of 5, I'll just go ahead and set array sub I j equal to I plus j, and then print array. So, right quick, Python 3 test py. No? Why? Why can't oh I know why. Array dot what is it to add something to it? Dot isn't it append? Append a new list to it. Alright. VI. And we're at time here. There we go. There, and then you have to do the same thing on that inner loop, right? You have to append instead of just setting it. I'm thinking PHP there, that's why. But yeah, you should be able to do that easily. Right. But if you want to use NumPy, you could do that as well.